This is an example of how to use Excel to do parameter estimation, where we take a function and fit it to data by automatically adjusting the values of parameters. So this example is a hypothetical case where we have a well that is being pumped while being held at a constant amount of drawdown. So when you do that, when you lower the water level in a well by a constant amount, the flow rate that comes out of the well is initially rapid, and then the flow rate decreases with time. And the initial flow rate and the way that it decreases with time depends on the aquifer properties. So here's our data set. This is time, and this is the flow rate coming out of the well here. And if we plot the data up, we see that it's initially large, and then it decreases with time over a 30-day long period. This kind of well is typically used in a formation with a relatively low permeability. An analysis of this kind of well is available in this form. This is an analysis that I did quite a few years ago, and it's available in a paper. And basically it says that the flow rate is equal to this function right here. So that's the transmissivity of the well, T. Delta P is the drawdown that's held in the well. And A and B and C and D are constants. And this TD term is right here. This is the dimensionless time, and you can see T there, that's the actual time, and then the transmissivity, there's the storativity, and R squared is the radius of the well, and they're the constants. Okay, so what we need to do is write this out as a function in Excel, and then fit this to these data by adjusting these parameters. So I've worked this out in an example, and let me go here and show you how to do it. The gray columns are the data that we just saw. And so what I did was to go into Visual Basic and write a function. And this is a function called discharge. Here are those constants. I need to use pi in this formula, so an easy way to create the constant pi is to take 4 times the arctangent of 1. It turns out that equals pi, and so that's what I'm doing right here. So here's the dimensionless time. I pass in the real time, which in the formula on the spreadsheet is just single lowercase t. And then there's the transmissivity, the storativity, the radius squared. So I calculate T, and then this is the formula that is on the spreadsheet. And the way I calculate this is I could write that formula out all in one. Let's see, this formula here. I could write this out all in one line, but the way that I've chosen to do this is a bit more simply, and I break it up and write out 3 terms. So b divided by log t is the first term. Let me go and do this. So that term right there is C1, and this next term here is C2, and so on. So there's also C3, and then this term in parentheses here is this term in parentheses here. Okay, so returns Q. So that function is called right here, discharge. And what I've done is to put the parameters that I need to pass to that function over here. And what I did was to set up some names of these basically variable names. I did this by highlighting this column, which will be the name of the variable, and this column that will be the value that's written into that name. So here's what you do. Highlight those two columns and then go to Data. Go to Formulas and use Create from Selection. So click on that. And the default that it usually gives you is that the left column contains the names. We can set it up a variety of ways, as you can see by clicking here, but the left column contains the names and the right column contains the values. So I hit OK. And I've already done this, so we can go back and check out here the defined name. No, we don't want to do that, sorry. We want to go to the name manager, and this checks out and allows us to see the names that have already been set up here. So you can see that S has this value, and there's S, and there's the value, and T has this value, and so on. So this allows you to check out. It's a good idea to check, and after you assign these names, to make sure that it's done what you think it's done. So now, for example, now that we've assigned these names, we can say equals capital T, and it gives us this value here. So if I change it over there to say 0.2, then it changes it there. Okay, so this is really just kind of making life a little bit easier by now allowing us to use these named variables instead of the cell references. So if we go back here to the function, you can see what I've done is write out the function name, and then this is the time. So the time is over here in this column. So I refer to that column with this A3. And then these are the different values that I have to pass into the function to calculate Q. And what I'm doing is using these variable names. Okay, that's how I can write in radius, because I've defined it right there. So when you do this, it's really a good idea to check the first time you use it by going, let's hit escape, going into Visual Basic, and I'll put a break here, F9, and go back here to the worksheet. And now let's try running this function. And now I'm just going to check. So trans has a value of 0.2. Let's see. There we go. So trans is 0.2. That's right there. That's right. S is 0.001. That's right. Radius is 0.1. Good. Del P is right there. That's 3. So we're good. We've passed the right values into this function, and so everything seems to be working okay. Okay, so what I've done now is to let me calculate this again. So what I did was set this up and then copied it down here, and that calculates the discharge, this function that I wrote, at each time. This cell reference here gets incremented, but these guys aren't incremented. They're just copied down. So this is my predicted value, and it's shown here in this black line. And I can change the value of t here. If I make it 0.1, you can see that it gets a little bit closer. So I could actually go and do a little bit of parameter estimation just manually. Say make it 0.7. That's getting closer, and I could adjust it accordingly. We can experiment around with that here in just a second, but let's look and see how the rest of this is set up, because even if we're experimenting, we would want to have a way to see how good we're doing other than just by looking at it and doing visual inspection. So I'm going to set up my estimates of goodness of fit. And the first column that I'm putting in here is, well, this column D is the residual. It's just the difference between the predicted value and the predicted value here and the data. And then, so it's just the difference between those two columns. And then the next column, E, is the residual squared. And then down here, I sum this whole column here. So this cell in row 33 is the sum of the squared residuals, or sum of squared errors, right there. So we saw that that is one measure of the goodness of fit, and indeed that's what we'll be using. We also want to calculate R squared. So R squared is going to be 1 minus the ratio of the sum of squared errors to the sum of squared about the mean. So what I did was to come back here to this column. This is the data, and I calculated the mean right here. So average is a worksheet function, and I just took the average of this column, and that's the average right there. So this column here, F, is the difference between the mean value and this data point, and then we square it. And you notice that I've got these dollar signs associated with the B33 cell reference. That makes so that when I copy this, the cell reference does not get incremented. So I copied this down, and so this is all the well, it's shown right here. It's the average Q minus the value of Q squared. And then if I sum that right here, it's not highlighted with a color, but we can see the formula. It's summing these square values, and so that term right there, that sum is the sum of squared of the about the mean. So here's R squared over here. This is 1 minus the ratio of the sum of squared errors divided by the sum of squared of the mean. Okay, and you can see that it's a large negative number that indicates that poor fit. Okay, so now we're ready to go with our parameter estimation, and we could return to this estimate that just works manually, and we could say try 0.3, and I guess 0.3 now is too low. See, I have this range set here, so or 0.03 is too low. It plots off of the plot. There's 0.04, so we're still too low. We could try 0.05, and yeah, wow, look, 0.05 is pretty good. Okay, so we're starting to, just by trial and error, home in on the correct value. Okay, so we also want to use S in the fit, and we want to be able to do this automatically. So if we, well, I didn't point this out, but if you guys try this on your own, adjust the value of t and look at this sum of squared errors. See, it's actually a fairly small number right there. And if we change this to say 0.06, the fit gets worse here. This gets to be a bigger number, and R squared is here it's a large negative number. Let's try that 0.05 value again. It's probably going to be closer to 1. Yeah, look, now it's really close to 1. Okay, so it seems like we are getting, these guys are giving a pretty good estimate of the goodness of fit. They're functioning properly, and so what I want to do now is show you how to implement a capability within Excel for doing this automatically. So go to data, and click on Solver. And if you don't see Solver here, then what you need to do is go here to File and go to Options, and Solver is an add-in, so click Add-in and see it says, let me see, where is Solver? There, Active Application Add-ins, there's Solver. So that's what you should see. And if you don't, then you should click down at the bottom of the page and you get a little pop-up, and there's the checkbox for Solver add-in. So you should check that, and also check these tool packs. The Euro currency tool we won't be needing. Okay, so if you do that, then this should show up. Solver should show up, and if you click on this, then you get this screen, and this will implement a fairly powerful nonlinear optimization package within Solver or within Excel. And so we need to tell it how to do its thing. So the first thing we have to tell it is, what is the objective? What value, what cell reference are we going to be using that is defining basically now the goodness of fit? So I've said E33, and that's this cell right here. So click on that, and then in this line I say that I want to minimize that. So what my objective now will be to make this as small as possible. I think actually that the default is that this gets checked. So if you don't check minimum, if you check maximum, then this will go away from the solution you want for the poorest fit possible rather than the best fit. So just keep that in mind. You need to check minimum, and then you need to tell it what variables, what cells to change. And so if I click on this, what I did was to highlight these cells here, and since I'd already defined these as names, Excel goes and recognizes the names as T and S. And then I need to, for this problem, and a common thing that is needed is to put constraints on the values of the variables. As it turns out, one of the things that can cause problems is that as the analysis searches around for good combinations of variables, it can go into it can try values of variables that can't really be calculated. If for example it uses a negative number and tries to take a log of that number, then that will create an error and the program will stop running. So what you need to do is put constraints on the values of the parameters so that you can't get into areas that cause problems like that. It also could be that the value of the parameter is so far off that the program can't find its way to the best solution. So the way to do this is to click Add and give it what the cell reference is. So if we wanted to put a constraint on you're going to be putting constraints on the variables that you're changing. So we could put another constraint on T. So click on that one and say T has to be less than 1,000. So that should be now showing up here. Yeah, so now what I'm saying, I already put in that T has to be greater than 10 to the minus 5, and now it has to be less than 1,000. So I've kind of bracketed the value of T in this way. And that's often a good thing to do, to bracket the variables. This new value, or this new version of Solver, has this checkbox where you can make the unconstrained variables non-negative. That's essentially what I'm doing here with these constraints. What would happen in the earlier version is that solver would go in, it would make these parameters negative, and that would cause it to crash. So it's possible that I could get rid of these constraints and just use this checkbox. This is new, but at any rate, we'll keep this for now, and that's the setup. You really just need these things. You need an objective, something you're going to minimize or maximize. You need to tell it what you want it to do, minimize or maximize. You need to tell it something to change to do this minimization, and then you have to put constraints on these things that you change. Once you have that, there are some options that you can try experimenting with, but I would try to solve right now. So we get this results, and so hit OK, and there is the results. And the fit that we started with was pretty good. This is a little bit better. It went from 0003 to 0001. So let's though try it a little bit further away, just so we can really be convinced that this is doing something meaningful. So let's say we put it at 03. Well, let me put it at 0.07 so we can get it up here so we can see it. Okay, and then S, let's put at 0.001. Alright, so then we'll try solver again. All this setup is the same. Hit solve. So, okay, before we do that, let's look. The sum of squared errors is 0.43, and R squared is minus over 100. So hit solve, and well, we notice here too what the data and the function are like. So hit solve, and it looks a lot better. And so we hit OK, and now we're back to that solution 0001 and 9667. It's not fitting perfectly because you can see there's a bit of noise in the data, and that's kind of typical. Okay, so we've got this worked out. One thing that's important to do is to try different starting values for your parameters, because what can happen is the function the solver routine can go and try to find the best match, but in doing so it heads in a downhill direction and reduces this value, but it may not really go all the way. It may get stuck in a local minimum. So one of the things that's good to do is to try different starting values. So let's try something that's on the low side. So let's try 0.01, and we'll run solver again. This is yep, so we get back here to the same result, 0.051. So that looks good. Now one thing I noticed, let's try a value that's quite high. So let's try a value of 1 for the transmissivity. And we'll go with solver, hit solve, and back to the same result. So that looks good. Let's try it even larger. See if we can cause some difficulties. So now it's up to 100, and so now we're way off. Hit solve, and yeah, it's still doing it. It's still coming back to the right value, so that's good. One thing though that I noticed in doing some numerical experiments is that solver would go and improve the estimate, but it wouldn't really go and go all the way. It would converge or stop running before it got to this value. But if I ran it twice, then essentially use the first run as an initial guess for the second run, then it would converge all the way. So you might consider doing that. In any event, what you'll find is that certainly for some problems, it'll be important to have a good or reasonable initial guess. If the initial guess is too far off, then solver may have difficulties finding the right answer. Let's try changing S as well. So let's give this one more try. No, boy. Well, actually, notice here that's a little bit. That's 0.95 and that's 0002. Okay, so this is a bit of an example. It's hard to notice here, but we haven't really gone all the way and have as good a fit as last time. So let's try running it again. And now we see, now it's 966. Okay, so we have improved the fit a little bit. So keep that in mind. I guess really two things. Try these different initial values and see if you're converging to the same value, and try adjusting the initial value to get close. In some cases, for one of the homework problems, you can have combinations of values that are so far off that solver just really can't advance, and so then you get the parameters that returned that are the same values that you start with. Okay, so what you need to do for homework is set up a problem, basically the same problem, and also then try doing a similar problem with a different function. But the basic procedure is going to be the same. I would put the data here and then set up these columns with the appropriate function, do the residual, square it, do the determine the mean here, and the difference between the mean and the value squared, and so on. So just use this worksheet as a template for other problems involving parameter estimation using solver. This ends up giving you a very powerful technique because the optimization routine here is really quite good, and we have a wide range of functions that we can develop using Visual Basic.